Good afternoon, everyone, and thanks for being here. Thanks for making me the last victim. I'm super excited to share some of the amazing work I've been doing, my team and I have been doing for the last 2 months, which is on DeepRoot, a deep reinforcement learning approach for dynamic network routing optimization and software-defined network on Chameleon testbed. So Chameleon is just a large-scale cloud infrastructure which supports computer science research and which is funded by NSF. So it basically is connected via a 100 gigabit link, and it supports, you have access to bare metal nodes, and it supports GPUs, FPGAs, and etc. So the ESNet is a high-speed network serving thousands of DOE researchers and collaborators worldwide. But it's becoming more complex as we grow. More than 40 DOE's Office of Science labs and over 140 research sites are directly connected to the ESNet, which means our network is complex and dynamic and will continue to grow, basically. But things like delay, traffic congestion, latency will jeopardize applications and prevent us from achieving our science mission. So the goal is to develop a Google map for ESNet, where the most optimal network route is selected, to use to transfer data from source to destination, thereby avoiding traffic. I'll give you an example. Let's say maybe someone from the HEP community, high energy physics. You've done huge scientific experiments here at Berkeley, and you need to collaborate with your collaborator maybe somewhere on the East Coast, maybe Boston, for example. How does the system know the most optimal network path to take from Berkeley to transfer those petabytes of data from Berkeley lab down to Boston? As scientists, we care about time, right? So time is really important for you to maybe transfer data across 2 distributed geographical locations. So it's also important to note that the ESNet traffic volume is growing twice the rate of a commercial internet. Take a look at ESNet traffic like 30 years ago, where the total ingress traffic was a little bit less than 25. It's been projected that the total ingress will increase exponentially by the order of magnitude in the coming decade. So the question is, how will ESNet cope with this challenge, considering the fact that the network has different traffic requirements, different quality of service, different bandwidth size, and different time-based deliveries? And this leads us to our problem statement. This is a problem we face in real networks, whereby we repeatedly deal with congestion. So if you visualize the network like the network of road systems, you will continuously have this, where everyone is trying to use the same pathway simultaneously. And this is even more evident in the peak versus the non-peak hour period, where the use is more. So our approach is to use AI and machine learning to improve real-time data transfer to avoid traffic congestion on ESNet. I'll give you another example. Anytime I'm going to San Francisco Airport from Berkeley Lab, I always use the Bay Bridge. I'm sure a lot of people use the Bay Bridge here, right? So what happens so imagine there's a crash. And when there is a crash, only a single lane was opened. Ideally, under normal condition, it should take me maybe, let's say, about 45 minutes or 1 hour to get to the airport. But because of that crash, you should budget like 3 to 4 or even 5 hours to get to the airport. So picture that in a more sophisticated and complicated environment like the ESNet network, which connects over 140 research sites, data transfer, different traffic requirements, and all sort of things happening behind the scene. So our motivation is basically to use AI to solve traffic congestion in an ESNet network. So currently, we have, network currently uses 2 main algorithms to calculate from source to destination pathway. One is to use a more centralized approach, which is the shortest possible route, which is the Dijkstra algorithm. And the other is to use the Bellman-Ford, which also is uses shortest possible path, but with the routers only knowing its neighbors. So our motivation is, since our network will have a more software-defined network capability, can we have an improved way compared to the existing algorithms we have that will take care of things like dynamic traffic changes, complex network, and etc. So, and this leads us to the current network research area, which is path computation problem, which is a current active research area. Major players like Google and Amazon have developed their own algorithms to control their own traffic. For example, Google has developed B4, while Microsoft developed Swan, which basically reads in traffic to make decisions. In data center, for example, you have existing solutions which include Hedera, Micetrap, and basically which prioritizes mice flow in data center. Our approach is unique, which is basically combining a unique machine algorithm with the PCP problem, which is path computation problem. And at the end of the day, we want to be able to improve data transfer time and also to avoid traffic congestion. So the goal of my research here is to investigate deep reinforcement learning algorithms for optimizing flow routing decisions, which we believe will help network engineers to understand performance behavior and to know the most optimized network path to take when scientists are conducting huge experiments. So, introducing you guys now to the reinforcement learning concept, it was inspired by the Atari games, basically. So I'll give you an example. We have an environment, let's say the Pac-Man game, or maybe the maze problem, right? And we have this cute-looking agent, which is our AI, trying to interact with the environment. So it performs an action, which basically means it's interacting with the environment, then it reads in a state of the environment, then gets a reward. So one good thing with reinforcement learning is it allows an agent to learn by interacting with the environment. So as an agent, it takes an action, interacts with the environment, reads in the state, and gets a reward. It takes an action, interacts with the environment, reads in the state, and gets a reward. And this continues over time. And over time, it learns the most optimal actions to play, basically. So when it does that for a very long period of time, it will be able to know what is the most optimal action to take to get the maximum reward. But how does this algorithm learn? How does the agent learn, basically? I've talked about the agent, then how does it learn? So I'll give you an example of the maze problem. Again, I love this robot. So we have a cute looking robot who is trying to make his way to San Francisco Airport. So right now, the agent has two ways to go. It can either go up, which is vertical, or it goes right, which is horizontal, right? So if you look at it this way, if it decides to go right, it's still the same number of boxes that we get it to San Francisco Airport. And if it goes vertical, same boxes because it's just 1, 2, 3, 4, and 1, 2, 3, 4. So let's introduce some numbers to make it more interesting. So if it decides to go right, it's still the reward, the value it gets is 0.73, and if it goes up, so that makes sense, right? Because it's the same number of steps. But what happens if the agent finds itself here? At that point in time, it has numerous options, right? It can either go vertical or it goes horizontal. These are all actions. It's all performing an action and interacting with the environment. So basically, if it goes vertical, that's good news, right? Because it's going through San Francisco Airport, which is the main objective. But what happens if the agent decides to go right? Clearly, it's going to end up in where? Hell. But we don't want the agent to do that, okay? So the main idea of the algorithm is it plays a random action, it changes the states, it gets a reward, we compute the temporal difference, and we update the Q values by applying what we call Bellman equation. And all these computations are being stored in somewhere which is called the Q table. But remember, before applying all this algorithm, we need to train it in a simulation environment. And one of the simulation environments we used is the OpenAI Gym. Technically, it's called the Gym, but it's been coined from the OpenAI. So the OpenAI is just an environment where you test your simulators, you test your algorithms to see if your RL, reinforcement learning algorithm, is actually learning well or not. So in converting this to a learning problem, we need to define our state space. Everyone that knows, anyone that's familiar with reinforcement learning knows one of the most difficult tasks is to basically define what your state space will look like. So as a starting point, we defined our objective, which is to reduce the flow completion time, which can be achieved by maximizing bandwidth utilization during heavy traffic. And also, we defined our action space as which path do I utilize? So the guy from HEP has conducted an experiment, but the system has multiple paths, traveling from LBL to Boston. It can go through Chicago, it can go through Atlanta, it can go through Washington. How does the system know which is the most optimal path to take during maybe critical conditions like traffic conditions? Then our observation space is basically what's the current bandwidth, what's the available bandwidth, and what's the path chosen. And our reward, which is the most importantly, is when we're taking the right step in the right direction or when we are taking the wrong step in the wrong direction. So the whole idea is for the reward, when you're taking the right step in the right direction, you get good rewards, right? But when you're taking the wrong step in the wrong direction, you get a bad reward, which is the example of the robot going to hell that I gave earlier. So in order to demonstrate our idea, first of all, we did it on a simulation environment, which we used OpenAI Gym, but we wanted to show a proof of concept. So we did it on an emulation environment, which we use Mininet, basically. So Mininet is just a network emulator where you use with a lot of open full switches, and you simulate what you want to simulate. Then we also used Chameleon to test this on real networks, basically. So like I said, Chameleon is just a test bed which supports computer science research funded by NHS. So I have a question for the audience now. If you are a scientist based at LBL and you want to transfer a huge amount of data to your collaborator at Texas, so Chameleon has two sites. We have one in Chicago, which is here, and one in Texas. So if you want to transfer data on visual inspection, where do you think is the fastest route to take? Because right now I have 4 paths, path 1, 2, 3, 4. Where do you think is the fastest path to transfer data from path 1 to 4? Anyone? If you're going to transfer data from Chicago going to Texas. Clearly it's path 3, right? On visual inspection, because that's the shortest path. But let's see what our agent will say. But the agent selected path 1. Why? Because we have some assigned parameters, which were the dynamic conditions going on behind the scene. So it selected path 1 because it has the highest bandwidth and also the lowest latency. So that's the whole idea. At any point in time, we want this system, we want our agent to be able to detect what is the most optimal route, taking into consideration some of these dynamic traffic conditions happening behind the scene. So, and this is how the network, and to give you a feel of how the network emulator works, this is basically how it does. You have the agent, you have a scientist at LBL trying to send data to maybe Kansas, and it has multiple routes. So at this point in time, we can see that the agent is exploring. It's trying to, there's a lot of data being sent utilizing multiple routes, right? It's going through Sunnyvale, it's going through ELPA, and all that. But over time, you will realize that this traffic will now be sent only using one path. So the first part is the learning phase. After it has learned the most optimal route to take, based on the hidden dynamic traffic conditions and the latency and bandwidth, then over time, it selects the most optimal. So if you look at it now, right now, it's done the learning, and it's now selecting the most optimal path, basically, which it says, according to the agent, is saying that's going to be the path that's the optimal. So in comparing network utilization in different multi-bandwidth algorithms, we compared it with 2 main ones, which are the basic RL algorithms. The first one was the random, which basically just we run the simulation and we see which path it's going to take. While the UCB, which is the upper confidence bound, we also got the result. But our observation is most of them still select one path, right? And that's a bottleneck, that's a problem. Recall the example I gave you guys about Bay Bridge. If everyone in this hall utilizes Bay Bridge, Bay Bridge, Bay Bridge, Bay Bridge, and there's a crash, there's going to be traffic congestion. So that's one of the limitations of these algorithms, which might still lead to possible traffic congestion. But how do we solve this problem now? So we now went ahead to introduce deep learning, because we believe deep learning will be able to take cognizance of all the hidden traffic conditions in a complex environment like the ESNet. We believe deep learning will work better, which are some of the things we believe it's going to avoid traffic congestion and etc. So this is the first stage of the simulation, and this is how it works, whereby it learns and it selects the most optimal path. So how do we now add deep learning? So the DQN agent here is added, right? So I still love this example. I'm still going to give the example for the maze. So right now the maze is at point 1, and it's still trying to go to San Francisco Airport, right? So let's make it more interesting. Let's add some axes. At this point, the agent is here, x2 equals to 1, and x1 equals to 1, right? What happens if the agent decides to go up? If it goes vertical, is my mouse showing? Sorry, okay. If it goes vertical, x1 will be equals to 2 here, and x2 will still remain 1, right? So in each state it goes, when it changes the state, that will be a new state, and those are generating states, right? So remember what I told you, performing an action, which is a state, it gets a reward, interacts with the environment, gets a reward, right? So over time, it learns the most optimal path. But the interesting thing we've done here is we now feed the states we get into our deep learning, we now feed these states as our input for our deep neural network, basically, whereby the state goes in, does the computation, then we have our prediction. I will explain a little bit in the next slide. So at the end of the day, we came up with this model where we have our DQN agent interacting with our environment, which is a network environment, performing an action, getting a reward in a particular state. So our argument here is deep learning will carry out a lot of, will be able to account for a lot of dynamic and complex scenarios. So but how does this deep learning now work? That's the next question I'm going to get asked, right? So the inputs, like I said, are the states. Each time the agent changes, it gets a new state, right? X1, X2, X3, like that. So the inputs are the state, which is basically a vector. So it goes through our neural network, and it predicts the Q value. Remember, this Q value are the quality of value. So if it takes the right step in the right direction, it gets a good quality. And if it takes the wrong step towards hell, it gets a bad value, basically. So it does that for Q1. It does that for Q1, and we also have a Q target for 1. It does that for Q3, we have the Q target for 3. And it does that for Q4, we also have the Q target for 4. And at the end of the day, we now compute the loss. The loss is basically between computing the loss between the predictions and the new target over the whole batch, right? And this doesn't stop there. We now back propagate the loss error back, and we now update the weights through stochastic gradient, basically. So this is going to continue, and the argument is with this whole process, is going to be able to account for a lot of dynamic traffic conditions, because we've not even included things like throughput, jitter, higher bandwidth, lesser bandwidth. These are all things that affect what determines what the fastest route is going to look like. So we trained this over 100 episodes with both random and DQN, and the good news was that when we trained with random, we got there was no learning was not evident, basically, because the mean score was negative. And remember, in any reinforcement learning, you need to get a good reward. So we trained it using DQN, just over 100 episodes, and we got this result, basically, where there was an upward trend in the cumulative, in the scores that it gets, and which shows that the mean score was also positive. So remember what I told you guys, when you take the good step in the right direction, you get a good quality of reward. When you take the wrong step in the wrong direction, you get the vice versa. So we didn't stop there. We went ahead to train this over like more episodes to see whether there's going to be anything. So remember what I told you the last time. If you look at from 0 to 400, that's basically the learning phase. And that's why you didn't notice anything. But when it gets to between 400 and 600, we notice there was an upward trend, basically, right? So maybe at that point in time, the agent is beginning to know what is going to be the most optimal path for me to take to maximize my reward. So, and we call that the warm-up region. So we zoomed that a little bit out, and we did the rolling mean, where we really confirmed that between 475 and 600, we had an upward trend of these scores per episode, basically. So we did a cumulative reward to see how things are going, and we compared both the Q-learning of the initial situation, the random, and also the DQN, and it was clear that the DQN was always going up. So these are all preliminary experiments, and we believe when we now move to a more sophisticated environment where we have different parameters and all that, this definitely will play a role. So we compared the random and the DQN, and we still observed that the deep root was still the DQN was still giving us a better performance overall, which is basically the score per episode. So in conclusion, we have combined AI and ML and controller decisions with the goal of improving bandwidth utilization and minimizing flow completion time to all possible paths. So remember, like I said, as scientists, we care about time, right? So our agent uses, at the moment, a single queue network with basically experience replay. We believe this presents a new research opportunity for advanced deep reinforcement learning, and in the future, we will introduce much more complicated parameters like higher delays, bandwidth, throughput, and more complex dynamic traffic conditions, and see how it affects the overall performance. And lastly, we will explore much more advanced deep reinforcement learning algorithms like the double dwelling queue network, and also policy gradient methods like Actor-Critic and DDPG. So I'd like to acknowledge my PI and Paul from the Chameleon Project, Nandini, and Dr. John, who's our group lead. Thanks for listening, and I'm open to questions, comments, feedback, and yeah, that's the end of my presentation. How many minutes did I spend?
Oh, sorry, can we go to slide 17? I think it's slide 17. Yeah, sorry, 18 here. This
Yeah.
So you're certainly lower on average, below 400.
Yeah.
And the trend is higher once you get after 600, but the variance is now a lot higher as well.
Yeah.
So do you know, you have sort of two overlapping distributions there, right? Do you
Yes.
know, how frequently you are performing better in the second half?
Yes, so exactly. So that's what we've observed, right? Basically, this determines whatever the parameters you've set, maybe within your environment. That's one key thing that contributes to this. The other side, what we observed was it was performing better in the second half, and that's why we did the rolling mean, just to see what the upward trend was, basically, right? And we noticed that from 0 to 400, even though we have some overlapping, at that point in time, what our belief is the agent is actually learning at that point in time. But when the score started increasing over the episode, we realized that our deduction was then it's learning better, because that's the whole idea behind reinforcement learning. Remember what I told you? If you take the right step in the right direction, you get positive rewards, right? And these whole rewards are the things that we train into the neural network, and it brings out the overall score back. Yes?
I'm not sure if you can answer the question, but I've seen this type of weird, I don't know, you call it phase transitions in the learning, and also other applications and learning paradigms. So why is it that after such a long delay, suddenly the system realizes something? Or is there do you have any insight in that, or is this too far away from you?
Yeah, so, this, I believe when we do some, based on literature, one way to correct, because this is actually a problem, but one way to correct this is basically readjusting some of your parameters which have been designed, because all these things are basically based on the scores you get on each episode. So on each episode, we have different actions. So let's say on the first episode, maybe the agent can decide to take 10 or 20 different random actions, right? And with all those actions are associated with maybe a particular reward. And those rewards now get cumulated to become calculated as each cumulated reward per episode. So there are some instances where we believe there's not going to be learning at some point, and that's what we observed in our emulation during the mininet I showed you. At some point, there was no learning. There was no learning because it was just exploring. Then after a bit of long time, which was really half of the simulation, then we realized it picked up. So we've done that in the emulation, and we had that same scenario, and we've done that in simulation, and we have this. But these are some of the things which we believe when we introduce advanced deep RL algorithms like maybe actor critic or DDPG, which has to do with policy gradient, that will solve that problem. Yeah.
So that flat area, that's because of your exploration time?
Yes, that's the exploration time, yeah. So there's exploration and there's exploitation. So think about the flat area as the exploration phase, basically. It's trying to explore and see what the possible combinations that will give it maximum reward, basically. Yeah.
We go to one of the previous slides where you compared Q-learning with the DQ1.
Yeah.
In that comparison, did you have the same Yes.
Yeah.
In the comparison between the Q-learning algorithm and the DQ1, did you have the same state for the Q and the DQ?
Yeah, exactly. I knew you were going to ask me that question. So basically what happens is we had the same state, but after running the experiment, we realized that we needed to change the state for the deep Q, right? Because the deep Q was a more advanced, was meant to take care of more dynamic traffic conditions, basically. So we never changed the state. We left the states the way they are, but this is something we will look at when we have a more complex scenario, basically.
But given enough compute time and everything, wouldn't the Q algorithm also eventually reach DQ1?
Yeah, it should, but when you have a more complicated scenario where you have things like jitter, throughput, higher bandwidth, lesser bandwidth, because the network is actually a system that is really dynamic, right? Things changes within the short period of time. So yes, given if you have enough computation time with a more complex scenario, then yes, my argument will be deep Q will beat Q-learning. Because Q-learning, the main challenge with Q-learning is there's no approximation, right? Everything goes on the Q table, and the Q table can overlap when you have a more complex scenario like maybe analyzing ESNet network. So, and that's our motivation behind trying Q-learning, because Q-learning takes care of that, and we just wrote a function which approximates the Q values.
So it's just because of the dimensionality problem that you have in Q-learning that you're using DQ1?
Yes, that's one reason. But at the same time, the analogy I gave was, think about those whole scenarios, the simple scenarios I've explained. Think about it in a more sophisticated environment like ESNet, where we have over 140 nodes, people doing high collider LHC experiments, trying to send with a lot of dynamic traffic conditions going on behind the scene. I'm sure Q-learning is going to struggle to really figure out what the most optimal path will be. So when it comes to deep Q, we believe with the introduction of deep learning, yes, it might get some positive result.
Would the Q-learning table be the same answer as the DQ1 table if you compare it? Shouldn't they come first? Yeah. Even Q-learning itself is an approximation algorithm.
Yeah, it is. But in terms of where you have a dynamic traffic conditions, I've read a lot of literatures which they've compared Q and deep Q, and yes, it doesn't come close. So these are all based on literature, and I have a published paper on this if you want to have a look. But like I said, this is this is just the initial phase of this experiment, which I started 1 month ago. So I'm happy to get feedbacks on this. Thank you.
Okay, I'd like to thank everybody for coming today and all the speakers again.